So up until this point, we have mostly been dealing with strong acids. And strong acids are ones that do this. When you get those into solution, you are going to make hydrogen ions and then the anion. This is my generic acid that I've been using a lot. And this is a one-way arrow. So by the time you get this stirred into solution and it's dissolved, there is no more of this. And everything you have in the solution is in that form. And these would be, of course, aqueous. You wrote lots of these equations one other day. Now the difference between a strong acid and a weak acid is that the weak acid will not completely do that. So we're going to write that this way. We're going to have an arrow that goes in both directions. So now we've got our acid over here, and notice that I haven't told you what the state is because this is our generic acid, and it might be a solid, a liquid, or a gas. But over here, because what we're doing in this equation is showing what happens in water, then these automatically have to be aqueous. This double-headed arrow that goes in both directions tells us that this is not happening, and that after we get all this stuff dissolved, we don't have only this. We have lots of this left because it will dissociate, but then it will come back together, and it'll dissociate, it'll come back together, and the molecules are constantly doing that. But at any particular time, only a certain percentage of them will be dissociated, and that's dependent on which acid we have. So, in addition to being able to write this kind of equation for acids, the other skill that I need you to learn is to be able to figure out what is the molarity of the hydrogen ion concentration if you know the percent dissociated. Now, one of the reasons that we're not going to do all kinds of other math with that this year, I explained the other day, because we don't know about logarithms yet, there's a limited amount of math we can do. But the reason I want you to do a little bit of math is so that you get an appreciation for how different a strong acid is from a weak acid. So let's look at this, and this is the kind of math that we can do because you know about percents. So it's a way that you can get a feel for the numbers without having to do math that's kind of beyond where you've gone in math class yet. So let's say that you are given that we're going to make an 0.10 molar solution of our weak acid HA, and that this particular acid is always 4.4% dissociated. In other words, at any particular time, 4% of this will be in this form. And those molecules will keep going back and forth, so it's not the same molecules all the time, but on average, this is the amount of dissociation we have. So given that you're already familiar with percents, you can do this fairly easily. We can say that, remember that percent is part over whole times 100. Now, in this case, the part is how much got dissociated, and the whole is how much we started with. So if we take this acid, now believe it or not, for a weak acid, this is quite a bit. You're going to see examples in your homework where there's a whole lot less dissociated than this. So this is kind of on the stronger end of weak acids. But that tells you why it's weak, right? Because up here we would have 100% dissociated. All right, back to the problem here. So the percent is given as 4%, and that's equal to the concentration of H+. So I'm going to put molarity of H+ over the concentration of the whole acid, which was given. So I don't have to actually put this in. That was given. So that's 0.10. And then times 100. So if I do the math here, I'm going to multiply both sides by this. So 4 times 0.1 is 0.4. And then I will have to divide both sides by 100. So 0.4 divided by 100 is that. So that means that even though we started with a solution that's 0.1 molar of HA, we only ended up with 0.004 molar hydrogen ions in solution. So that's why it's called a weak acid.